Hello. So in this video, we're going to look at exponential modelling. So real life questions based on exponential functions, right? So last time we looked at e to the x, right? So y is equal to e to the x. If we were to sketch this graph, then if I remind you, it looks like this. So it's a standard exponential curve that then slowly rises up like this, and it passes through 1. That's why it's e to the x. But also, a very helpful other curve to remember with this is e to the minus x. So e to the minus x is the other way around. It's a reflection. It looks like this. So it comes down instead of going up, okay, and it tends to 0 there. So that's why it's e to the minus x. And yeah, I may remind you as well that e is just a number. E is like pi, it's just a number. You can access it on your calculator. It is 2.71828 blah blah blah. It's an ongoing irrational number, so it's an ongoing decimal. So e, don't be afraid by e, it's just a number at the end of the day. It's an exponential. And so we have these two graphs, okay, and it's very helpful to remember what these two graphs look like. So e to the x and e to the negative x, okay, that would be very helpful for when we model, because a lot of real life scenarios will have variables that look or behave like these curves. So we call this exponential growth. So we call the first example exponential growth, e to the x. And the second example, because it's going down, e to the minus x, this is exponential decay. Anything that decays goes down over time, okay? So you might see something like it rises exponentially. This is what we mean. So it starts off slow. There's not much growth initially, but then it starts to pick up and then just rises and rises. Okay, this is what we mean by exponential growth. And there are many real life things we'll see in this in the questions, such as bacteria. Bacteria grow exponentially, they multiply rapidly. So initially you might have like just 2 bacteria, and then they just reproduce and grow, and then you've got thousands and thousands and millions. Same with viruses as well. It's important to contain viruses quickly, because then if it spreads and more people become contagious, and then more people get viruses, it could be deadly. So we need quarantine, because viruses are also can grow and spread exponentially. And so here we've got exponential decay. So examples could be like maybe in physics, something like half-life. So to do with like radioactive substances decaying or like diminishing, or like something like a car. The value of a car generally, its value over time decreases exponentially. So for the first few years of the car, the value drops down quite massively, but over time it starts to kind of level off. Okay, and so in general, we can model, right? We can model things exponentially, as we discussed, like with the examples. And so, what do we mean? What do we mean by exponential model? Well, we've already seen, for example, linear models with straight lines. So these are models of with the equation y is mx plus c. So it's a straight line effectively. That's a linear model, a linear equation. We saw quadratic models. So these are y is ax squared and bx plus c. So again, a quadratic sort of equation. So for example, when we saw like say someone throws a ball in the air, a ball will have this sort of trajectory, this in the form of like a quadratic curve, right? That's the path. If you throw a ball in the air, it would look like that. So that's quadratic models. Now exponential models, the equation we're going to use really, when what we mean by exponential model is y is going to be a multiple a, e to the bx. Okay, so this is the equation of an exponential model. There can be others, but this is usually the most general one. Okay, the typical one, right? So we can model various things that grow or decay exponentially with this model. Okay, so you might see perhaps an exam question say, give an exponential model for this. So you need to refer to this equation here. Okay, so yeah, and so we will be working with this sort of equation to model real life things. Okay, right, and so these terms A and B, they have meanings, right? So firstly, A. Now usually these models, it's with respect to time. So usually x is time. Okay, so if we have, for example, y is ae to the t to the bt, right? So x is t. Time is non-negative, which means that t is at least 0, cannot be negative. Time cannot be negative. So with these models, t equals 0 is the first value we can use. So if t is 0, then y is going to be ae to the 0, right? Because obviously bt, 0b, that's just 0, okay? If I put t 0. Now actually, e to the 0 is just 1, okay? You can put that in your calculator because anything to the power of 0 is 1, okay? So that means y is simply a. So therefore, the initial value, it has to be the initial value, right? Because t0 is like the initial, well, it's the initial time. It's the start of my like study, if you will. So a is the initial value. Okay. Now, what about this b then? This b. And so to see what the value of b represents, well, what's so significant about it, I'm gonna pick two examples. Okay. So for example, I'm gonna take e to the 10t, and so actually it's quite hard to see what the b represents in its as it is, right? E to the 10t. So if y is e to the 10t, it's hard to e to the 10t. It's hard to see what the 10 actually means, but actually the significance of the b part, this equation, ae to the bt, it becomes a lot more apparent when we differentiate. Okay, so then if we differentiated this e to the 10t, remember the 10 comes to the front, so it'd be 10 e to the 10t. Okay, I should say as well, it's not dy dx, it's dy dt, because obviously we got differentiating t, not x here. Okay, but actually notice that then we have 10e to the 10t, but actually e to the 10t is just y. So actually then the derivative is just 10y. Okay, so then again, remember that this is the derivative. Remember we looked at this in differentiation. It means the rate of change. So how much is y changing? Let's say every second or every month, every year, depending on what t is, right? It could be days, months, or years. So this is telling me that 10y, that actually y is being multiplied by 10 every second, or every month, or every day, or whatever. Every second y is being times by 10. So 1 second it's times by 10, then the next second times by 10 again, and so on. Or if we had to say like 2y instead of 10y, let's say, then y is being doubled every second. Okay. For example, maybe something like cell division or something like that. Obviously, cells replicate, right? Or bacteria or something like that. They double every second, right? And actually, you notice again, if we keep doubling every second, it's going to spiral. So anyway, we have 10y, so this is going to be by, right? Remember, b is 10, and this will always hold. Okay, you can spot then that 10y or by, 10 is the factor for the rate of growth then. Okay, so b is the factor of the rate of change, right, or growth, depending on what it is, but it's the factor for the rate of change. Okay, because the rate of change is the derivative, and you can see that 10 is indeed a factor. Okay, so that's what that means. Or for example, let's say if we had 1.01 y, now 1.01 is 1% as a percentage. So this, alternatively, if it's 1.01 y, let's say that represents a car or something precious, right? The value is increasing by 1% every day or every year or whatever it is. So this it's the factor for the growth, right? The factor of how much it's increasing by. So every year, if we had 1.01%, multiply it, it'd be increasing by 1%. Okay, every year, something like that. So that, hopefully you just get the gist of. It's basically telling me how much I'm increasing by. This b, right? It's basically the factor for how much I'm increasing by. Okay, now I want to look at this example here then. So now let's say we have y is e to the negative 10t. So that's b is negative 10. Okay. So again, if we differentiate it, you get the same result, that dy dt is going to be negative 10y, or negative 10 e to the negative 10t. So the difference here is now we have a negative 10 instead of positive 10. Okay. Now, what you need to understand as well with the derivative, right? We've seen that if the derivative was positive, that means it's increasing, right? But if it's positive, it's increasing. If it was negative, it's decreasing, right? We've seen that in differentiation. So that means the sign of the derivative tells me actually whether the function is increasing or decreasing, right? So actually, in particular, because it's positive 10y, this is growth, or it's increasing. Okay, but actually here it's negative 10t, negative 10, so it's a decay, or going down, or declining, right? Or it's decreasing. Okay, so when you're differentiating, you need to pay attention to the sign of the derivative. Okay, is it positive or is it negative? That'll tell me if it's increasing or decreasing. So if the value is going up or if it's going down, or something like that. Okay. Okay. Cool. So one final thing I want to talk about before we look at questions is this idea about limiting values. And I've come back up here because these graphs will help me here. So in particular, this e to the negative x here, you can actually see it's going down and it's going towards 0, right? What we can say then, that e to the negative x basically tends to 0 as x tends to infinity. Okay. Now that might seem, I guess, a bit, you can kind of see that, right, quite clearly, right? It's going to 0 in the long term, right? This graph here, e to the negative x, it goes to 0. It's the asymptote is 0, but x gets longer and longer to infinity. It's important to state that because questions will ask you what the limiting value of e to the negative something is. And so, for example, then, we are asked to find the limiting value, or the long-term value, of 10 plus e to the negative 2t. Okay, so as t is t's time, what happens to this expression as t goes to infinity, as time goes on and on and on and on? Well, actually, to work that out, we need to recognise, by using what we've just seen up here, that actually e to the negative anything, so in this case e to the negative 2t, that goes to 0, okay? Because of this graph here. Again, e to the negative 2t will have a very similar graph. It will tend to 0 in the long run. So that goes to 0 as t tends to infinity, which means that this 10 add e to the negative 2t will go to 10, basically add 0. So that will just go to 10. So in the long run, this expression approaches 10, okay? That is the limiting value. Okay, so I thought I'd go over that now here, okay, because you will often find like a 1 marker or a 2 marker explain what the long-term value or the limiting value of an expression like this, okay, and you almost kind of think of it as basically think of it as e to the negative infinity basically equals 0. Not technically correct, but you can think of it like that if it helps, at least at this level anyway. If you have e to the negative infinity, basically equals 0. So in the long run, it just reaches 0. Again, not technically correct, but if it helps, that's essentially the idea. That in the long run, e to the negative x tends to 0. Okay. So I'm going to look at some questions now, because quite a lot there. Let's have a look at applying this. Okay, so we're told the density of a pesticide is given by the equation P is 160 e to the negative 0.006t. We're first asked to use the model to estimate the density after 15 days. So again, time is days and the density is P. So if after 15 days, the density, well, we're going to sub t is 15 in, okay? So when t is 15, then p is going to be 160 e to the negative 0.06 of t, which is 15. And so actually at that point, we just put that in the calculator, okay? So 160 e, which is then to a power of minus 0.006 of 15, and so that would get me 146.228 blah blah blah, and that would be in milligrams per meter squared. Okay, that's the units. Cool. Right, okay, that's the answer there. Or we could round it, I guess, 146.2 milligrams per meter squared to 1 decimal place, but there we are. Part B then, so that's just substitution, right? So then part B, it asked me to interpret the value of 160 in the model. So again, remember my equation is 160e to the negative 0.006t. This 160, what does that mean? The significance in relation to what's going on here. So again, 160, that will stem, if we consider t to be 0, then P would be 160e effectively to the 0, right? This whole thing minus 0.006t, if I put t 0, it'll be e to the 0 overall. But that e to the 0, anything to the power of 0 is 1, so P is just 160. So actually that tells me then that T0 is the initial density. So 160 is the initial density of the pesticide. Okay. Cool. And that again refers back to what I talked about up here, where where A, the coefficient, right? The coefficient out the number outside of the exponential, A is the initial value. Okay, so that's what we're getting at there. Okay, so 160 is the initial density here. Okay, for part C, we need to show that the derivative dp dt is this. Okay, so dp dt is k lots of p. Well, actually, it's asking for the derivative then, right? So remember p, the expression was 160 e to the negative 0.006t. Okay, and so therefore if we differentiate dp dt, so that means the constant in the exponent, so in the coefficient of t, the exponent comes to the front, so the derivative will be minus 0.006 lots of 160 e to the negative 0.006t. Okay, and actually I don't think we should simplify this, because notice it wants the answer as a multiple of p. That's my k is a multiple, but actually observe that this bit is just p, so we can say that this is minus 0.006 of p. So actually therefore k is just minus 0.006. Okay, let's say instead you did expand it, right? Understandably, let's say you did expand it instead, so you did minus 0.006 times 160 to get minus 0.96 e to the negative 0.006t. How could we deduce k in this case? How could we deduce that this is a multiple kp? No, it's equal to p, a multiple p. So actually what you could do instead is, well, recognise that that still e to the negative 0.006t is part of p. So actually I could effectively rearrange it to say that p divided by 160 is still e to the negative 0.006t. And so then I could substitute that in to say that's going to be minus 0.96 of p divided by 160. And then that's minus 0.96 divided by 160p. And so then if we work that fraction out, minus 0.96 divided by 160, you indeed get minus 0.006p. There we are. So we can still get the same answer. Okay, if we did simplify it before you looked at the answer, you can still do it either way. But there we are. Okay, that's K. So part D then. We are asked to interpret the significance of the sign of the answer to part C, what we just did. So the sign means positive or negative, okay, effectively. So the sign of my answer, so again, as I remind you, my answer was the derivative was kp, so it's minus 0.006p. The sign is negative, okay. Or in other words, that means the derivative is less than 0. Okay, it's negative. So then think back to when we did differentiation. That means that p, the function p, is decreasing. Okay. And so what that means then, remember p is the density of the pesticide. So the density of the pesticide is decreasing. And so that's what that means, okay? And so it's decreasing by a factor of 0.006, okay? And that's what that means. Okay, cool. Part E, we need to sketch the graph of P against T. Okay, so I'm going to do that up here actually. So I need to sketch the graph that P is 160 e to the negative 0.006 t. Right, okay. So to sketch it then, you could recognise this as just a series of transformations. So you could do e to the negative t, then e to the negative 0.006 t, then 160 e to the negative 0.006t, and there's your answer. But actually, there's quicker ways of doing it by just spotting certain things. What I mean by that, so firstly, it's going to be t against p, right? P against t. And also, I already deduced that in part B, the initial value when t was 0 was P's 160. So that means 160 is going to be on my P axis here. the p-intercept. That's when t is 0. And actually, I also saw in part A that when t is 15, p is 146. So when t is 15, it's going to be 140. It's going to be somewhere there. Okay. So actually, you can see the curve, right? What's going to happen to the curve, right? Between these 2 points, and we know it's going to still be an exponential curve. It's going to go down because it's e to the negative something. Remember, this is e to the negative x. It goes down like this. So between these 2 points, it's effectively going to go like that. Okay, and that'd be my curve, right? So it's just a rough sketch, right? Rough sketch. And I could label this point, so that's when t is 15. Then p was 146.2. Okay, so that's the graph, alright, without having to do any wacky transformations. That's the rough idea. But t is time. Remember, time is always positive. So actually what we need to do is basically cut off the negative t portion. So we need to cut off the left side of the graph. If we do that, the graph we actually get, if we copy the positive part, well actually we won't have a negative t-axis. It will just look like this, okay? T and p. And actually p will be positive as well, because it's density. So that'd be positive as well. So actually, effectively, all we'd have is the positive part of the graph. Positive t, positive p. There we are. And then 160 is there, and then it has this sort of shape. Okay. And there we are. That is the curve. That is the curve. P is 160 e to the negative 0.06 t. Okay, as long as you get your y-intercept there, your p-intercept of 160, hopefully you can then sort of deduce what the curve will look like from that. It just tells you where you start in the curve, essentially. You could also, again, mark here, this will be 15, and then 146.2 if you wanted to, but there we are. Okay, cool. Okay, so again, you'd try and, with these sort of questions, if recognize what e to the x and what e to the t and what e to the negative t will look like. Remember, e to the t will be a positive curve like that. E to the negative t will look like this. So the graph has to loosely look like this. Okay, there we are. Anyway, so then it says the same volume of a different pesticide is applied to another section of field. The density of the new pesticide is known to reduce more rapidly over time. State the value of the original equation that should be changed to model more rapidly. Okay, right. So basically, there's a different pesticide now, and we're told the pesticide reduces more rapidly over time. So this idea, rapidly over time, this is talking about rate of change. Okay, so how is the pesticide, the density changing? Okay, that's rate of change. That will then hint to dp dt. Okay, well actually we computed dp dt, right? dp dt, we worked out in part C, was minus 0.006p. Right? Okay. So the function we've got then, p, this is effectively saying that the density, p, is decreasing by 0.006 every day. Okay, that's what that's saying. Decrease, so p decreasing by 0.006 every day. That's what that's saying. Okay. And again, it's decreasing because it's negative. Okay. Now, what it's talking about here is it's reducing more rapidly. So it's decreasing, but it's going to decrease more. What that means is then we need this to be more negative. So then, for example, if we changed it to, let's say, negative 2p. That's now saying that the p is decreasing by 2 every day. That's a sharper decrease, right? It's reducing more rapidly if we make it more negative, okay? So that's my answer. So the value of the original equation, that needs to be changed to produce a more rapid reduction, a more rapid decrease in p. This minus 0.006 has to be more negative. So it has to be like minus 2, minus 10, minus 100, but it'll decrease by a larger amount, okay? So therefore the answer is, hopefully that illustrated the idea, the answer is the value minus 0.006 must change to be more negative. And they actually do accept that phrasing, or you could say lower, or lower value. Because remember, lower value means you're going more negative. Because if you think about a number line, the lower you go, the more negative you go. So it's the same thing. But they do accept this phrasing of just being more negative. Hopefully you get what I mean by that. Right? So yeah, so then the value is more negative, the value, which means it's decreasing by more every day. Okay, so it would be a more rapid decline, okay, by changing that value. Okay, cool. So hopefully that made sense. So move on to another question here. Okay, so we've got some exercises. We're told that the population of a country is modelled by the formula P is 20, add 10e to the t over 50, okay, or a 50th of a t. There we are. Okay, so P is the population in thousands, and T is the time in years after 2000, the year 2000, okay. I always tend to highlight the units, okay, because they might catch you out, and it will catch you out here if you don't pay attention. So part A, we need to state the population in the year 2000. Well, that's when the time is starting at 2000, right? So that's the initial time. So T is 0, then P at that time is 20, add 10e. Well, a 50th T, 50th of 0 is still 0. But then e to the 0 is just 1. Again, remember, power of 0 is 1. So that would be P is 20, add 10. Lots of 1, so that's just 10. Overall, we get 30. 20 add 30. So P is 30. But that's the value of P. That's not the population, because the population is a thousands of P. So we need to multiply that by 1,000. So population is 30 times 1,000. And that'd be 30,000. Okay, and there we are. So again, pay attention to your units there. Part B, we need to use the model to predict the population in the year 2030. So, again, in the model starts at 2000. 2030 is 30 years after. So time in years, it means T has to be 30. So we need to add 30 years on. So then P at this time is 20 add 10 e to the 50th of 30. And so if we put that in the calculator, that will be I get 38.221. Okay. But again, that's the value of P. The population is in thousands, so I need to multiply this by 1,000. So population is 38.221 times 1,000, which would be 38,221. Okay, roughly. Okay. Right, cool. Part C. Now it's asking to sketch the graph of P against T for the years 2000 to 2100. So, interesting. Okay, so P against T. So again, we're going to sketch the graph P is, what was it, 20 add 10 e to the negative 50th t. So again, I don't really want to decompose it into a series of transformations. I don't want to sketch e to the 50th t, then 10e to the 50th t, then add 20 on. It take a lot of work. Instead, I can sort of just visualize what the graph will look like. So e to the 50th t, that's just e to the t effectively, broadly. So e to the positive t will have this sort of shape. It will go up, right? So that's broadly what the graph will look like, okay? Just the shape of the graph, it will look like that, okay? That's why I say you need to remember the graphs e to the t and e to the negative t, right? So e to the negative t, again, will go down. If you remember these two graphs, you'll be good, okay? But you do need to remember them. So the shape will look roughly like this, roughly, okay? So with that in mind, we can sort of do a sketch. Now, again, P and T are positive, okay? T's time, positive. P's population, positive numbers. So we only want the positive quadrant, okay? There, okay? We don't want any negative axis. The P against T, the other way around. There we are. So then if we sketch it then, well, firstly, we need to find the y-intercept. Where do we start? The p-intercept even. But we saw that in part A. We have some numbers already. We know that in part A, the initial population, well, the initial value of P, we're sketching P, right? P was 30 when T is 0. So that's the p-intercept of 30, okay? So it'd be there. So then you can kind of deduce that the graph is going to look something like this. Right, something like that then, as a result, okay? Okay. Right, and I also know, it might help maybe, that we have the additional data point when t is 30, p is 38. So when t is 30, let's say here, p is 38, so it's going to be somewhere there. So actually it probably looks something like this, okay? With these 2 points on there, okay? So 38.2, okay. Cool, so that's what my graph will look like. However, with this question, there's an additional thing to consider. That's the graph, that's what it will look like, cool, but it only wants it between years 2000 to 2100, which means the graph the graph is not meant to go on indefinitely, okay? Because it will go on for infinite years, but they only want it between 2000 and 2100. So that means only in 100, t is 100, okay? So after when t is 100, we don't want any more after that, okay? So there's a cut-off point, okay? So, okay, so 100, let's say that's going to be... t is 100. I'm trying to let's say it's somewhere there. I'm probably gonna have to adjust my graph a little bit to make that make some sort of sense. So it would look like that. Okay, something vaguely like that then. Okay, something like that. Okay, that's what my graph looked like. Something vaguely like that. Okay, so t is 100 is going to be there, but then that's my cut-off point. My graph needs to stop at that point, okay? There we are. So that's my exponential curve. So it's going to cut off at this point here. There'll be no more graph after that, okay? Well, how do I work out that point then? So again, how do I work out this point? That's going to be when obviously t is 100. So when t is 100... P is going to be 20 add 10 lots of e to the 50th of 100. So if we put that in the calculator, that will get me 93.89 or 93.9, let's say, to one decimal place. So that value there, if I extend the graph for P just slightly, that value will be 93.9. So So that coordinate is P is 93.9. No, sorry, T is 100. P is 93.9. So that it has a cut-off point because that is the year 2100. They don't want any more years after that, okay? So crucial detail there. Cool. Right. Part D then asked. I don't want to keep scrolling down. I'm going to do part D up here. So part D asks, do you think it would be valid to use the model to predict the population in the year 2500? Okay, so 2500, but these sort of questions, let's just see what happens, right? When T is, well, what value of T would it be? Because it starts at 2000, that's when T is 0. 2500 is when T is going to be 500, right? If I then substitute that into P, then therefore P is going to be 20 out of 10 of e to the 50th of 500. And so that will get me this number here, 220,284. Okay, 0.7. Okay, but I'm going to leave that there. Okay, I'm going to I'll round it to the nearest whole number, nearest integer. Okay, but also, obviously that's P. So then the population is going to be times by 1,000, right? And that would be actually 220 million. Extraordinary number, right? Nearly a quarter of a billion people, which is interesting. In 500 years, we've started with a population of 30,000, and then we've gone up to nearly a quarter of a billion in 500 years. Think about the UK. UK is what? 2025, I think our population is nearly 70 million in 2,000 years over that. So in 50 years, compare that, in 50 years, 500 years, sorry, with this country, apparently it's going to be a quarter of a billion. So it's like quadruple the current numbers we have, which we've garnered over 2,000 years. So it's an unreasonable number is what I'm getting at, right? So it's not really valid. So population is very unlikely to reach 220 million in 500 years, in a space of 500 years. Very unlikely. So not valid to use a model here. And there's my answer. Right, okay. So again, if you've got these sort of questions at the end, what happens if how valid is it for this particular point? Just substitute that value in and see what you get, okay? Now we've got this question. We've got this question here. Okay, so we're told that the number of people infected by a disease is n is 300. Take away 100, e to the negative 0.5t. N is the number of people infected, and t is the time in years. Okay, so part A asked, how many people were first diagnosed with the disease? So first diagnosed implies initial time, which is 0. So time is 0, then n is going to be 300. Take away 100, e to the, 0, right? E to the 0, because there we are. If we put that in, well actually we don't need a calculator, because that'd be 300. Take away 100 lots of 1, because e to the 0 is 1. So that'd be 200. And so that'd be 200 people. Okay, there we are. Cool. Part B then says, here we are. What is the long-term prediction of how the disease will spread? So that's talking about the limiting value stuff and the long term stuff I talked about at the start. And so we discussed up here that basically e to the negative x goes to 0 as x goes to infinity. Okay, so well in this case we have e to the negative 0.5t. So that will still go to 0 because it's a negative, right? Negative power. That will go to 0 when t goes to infinity. So this is the long-term prediction. This is long-term. Okay, that's when the time is basically going to infinity. Lots and lots of time. Okay, so the long-term prediction when t is large is because e to the negative 0.5t goes to 0, as we discussed, because the idea is that the graph e to the negative x, which looks like this, it goes towards 0, right, in the long term, as you can see, which means in the long term p will go to, well actually p will equal, in the long term, n, we don't have p anymore, we have n will go to 300, take away 100 of e to the negative 0.5t. But as we discussed, this goes to 0. So effectively, we substitute that in to get 300, take away 100 lots of 0. And so we left with 300. So in the long term, it will spread to 300 people. And so people, and you can think of that as the limit as well. So the limit of the spread is 300 people, okay, of the disease. But there we are. Okay, so that's how you tackle those sort of questions about the long term. So that's part B. Part C, we need to then sketch the graph of n against t. Okay, so again, remind you, this is my graph, this is my equation. So again, I'm not going to do all the transformations, I can do a rough sketch. So firstly, n and t are positive, so it's going to be again just a positive part, like this, t and n. And we also know that the intercept on the n-intercept, so that's when t0, the initial value, n is 200. Okay, so it's going to start at 200, let's say here. Okay, and I also know, and this is why part B would help me here, I know it's going to have, okay, well, I know it's going to be an exponential curve, right? It's going to look like this, or perhaps like this, right? It's going to have that sort of exponential flavour, right? That sort of shape. To help me again visualise the curve, we can also consider this point here in part B. As we've discussed, that as t goes to infinity, n is 300. So it's kind of like an asymptote then. If t gets large, right, if t carries on and on and on, the curve will tend to 300, okay? So what happens is it starts here at 200 and then it tends to 300. So the curve will look something like this. Okay? And so there we are. But actually we only want the positive part, so it look, if I cancel the first part out, it would look something like this. Okay? And that would be my curve, okay? A bit tricky that was, but yes, again, you don't need to consider doing all the sketches manually one by one. It'll take a lot of time. Just consider some points, right? So, some points on the curve, and then you can kind of like plot the curve between the points, right? In that sort of way, because you know it's going to be an exponential curve, so it looks like this, right? And yeah, and so the asymptote, it tends to 300. So yes, that's how I got that graph. Cool. Alright, so we've got some exam questions now. And they do love asking questions on this, so very important topic to revise. So I'm told that the value of a car is this formula here. So V is 15700 e to the negative 0.25t, then add 2,300, okay? And the time and the age of the car is t years, so t is in years. The price, the value is in pounds, okay? So we first need to find the initial value of the car. So again, initial means the time is 0. So if I do time is 0, then the value will be 15700 e to the, basically e to the 0 when time is 0, add 2300. Then that'll be effectively, this will go to 1, right? E to the 0 is 1, so we've got 15700, lots of 1, add 2300. So if we work that out, I get 18,000. Okay. So initial value in pounds. Initial value is £18,000. Okay. Part B. I'll do part B up here. Then I've not got much room. Part C. Obviously, some of it was cut out. You won't be able to do the other parts of the question yet. But part C. We're told the model predicts that the value of the car approaches but does not fall below A. That's so set the value of A. So this A is the limiting value. Okay, it's heavily hinting towards the asymptote. Okay, that's what it's kind of saying. So obviously, again, an exponential curve has an asymptote, right? It tends towards an asymptote, right? This is the limiting value. Okay, so to work that out again, the limiting value, it's ongoing, so it's basically what happens in the long term. Okay, so that happens when t goes to infinity. Okay, and so again here we got e to the negative 0.25t, so that will go to 0 again, because anything like e to the negative x for any x goes to 0. Remember, that's the exponential curve. If it's negative, it goes to 0. And it goes to 0 when t as t goes to infinity, which means that v will go to, then v will be in the long term 15700 e to the negative 0.25t, add 2300. But obviously we know that this exponential goes to 0, as we just said, so that it will go to 15700, lots of 0, add 2300, so that's just 2300, right? So that is my limiting. That is the limiting value, right? That is sort of like the lowest value. So that is A. So that means A is this value here, because as you can see, that initially at the start is £18,000. That's the value, but the value of the car goes down, and so eventually the car will go to 2,300 as a value. Okay, and it won't go below that. Okay, so yeah, so that's again the idea of about setting t to infinity, and so the exponential goes to 0. Okay, again, make sure you're aware of that. Don't lose marks like this. Okay. Part D, then the next part, state a limitation. Okay, so again, you have to just think a bit more like critically. So I mean, they didn't ask you to work at A for no reason. So the sort of the long-term value, right, of the car. So the car, obviously the value goes down over time. This is the lowest value. So you could say perhaps that this is higher than usual. Think about it, in like say like 100 or 1,000 years, like the value of the car after like 1,000 years would probably only be like a few £100 of that. So it's not going to be this much, but alternatively, maybe you could say it become vintage, and actually it would shoot back up. So it might go down initially as the car ages, but becomes so vintage it might then shoot back up in value. So you could say many things. You could say model does not account for the value of car increasing as it becomes vintage. Or you could say that £2,300 is maybe too high for a car that just goes to scrap or something like that in the long term. After like 1,000 years it'd be unusable. Would you pay 2,000 for a car that's unusable? I don't know. Alternatively, you could also say the many things you could say. Alternatively, the only thing that affects with this equation, the only thing that affects the value V is t. T's age. What that's saying is basically, say like you have two cars. Say like one car hasn't been used at all, maybe once in 10 years, hypothetically. And let's say one car that's been used every day for 10 years has a lot more mileage, it's a lot more run down. But according to this formula, it doesn't take into account other things like mileage, only age. So two cars identically the same age, but mildly different uses. Maybe one car's crashed more, one car's broken down more, one car has more mileage, it's more run down, so it would have lower value, but the model doesn't account for that. Also doesn't account, so I'm going to say also does not account for other factors. Such as mileage, or if the car's crashed or broken down, or how many times it's crashed. Many things you could say. Okay, but there we are. So that's the sort of gist of that. Okay, so I've got this question here. So here we're told the height of a plant is h is 2.3, take away 1.7 e to the negative 0.2t. First of all, we need to find the height of the plant when it's first measured. So hopefully it's not to deduce, a very sort of formulaic the way they ask. So firstly, they want to ask for the initial value. That's when t is 0. So when it's first measured at time is 0, the height is 2.3. Take away 1.7 of e to the effectively to the 0. Okay, e to the 0. So then that would be 2.3 minus 1.7. Lots of 1. So then if we do that, that would be 0.6. Okay, and that what are the units? Height in meters, t years. Okay, so it's in meters. Okay, and so there we are. Cool. Part B then says show that exactly 4 years after it was first measured, the plant was growing at approximately 15.3 centimeters per year. So it's not asking for the height per se, it's asking for the height per year. That's a rate, okay? Anything to do with per year or per minute or per second, that's a rate, okay? That's a rate. So that's how the height is changing over time. That is differentiation, okay? That is alluding to differentiation. So we need to compute the derivative, so dh with dt. So we know that h is 2.3 minus 1.7 e to the negative 0.2t. So if we differentiate this, so firstly 2.3 is a number, it's a constant, that will go to 0, okay? So then that'd be 0, or just leave it. Then minus 1.7 e to the negative 0.2t. Again, the negative 0.2 will then come to the front, so it'd be minus 0.2, lots of minus 1.7 e to the negative 0.2t. And so then, if we work that out, we can simplify that, because minus 0.2 times minus 1.7 is positive 0.34 e to the negative 0.2t, and that's my derivative, okay? And so then if we want to find the rate is increasing at 4 years, we need to substitute t is 4 into here, okay? So at t's time is 4 years, the rate derivative is 0.34 of e to the negative 0.2 of 4. And so if we put that in the calculator, we get 0.15277, blah blah blah. And so what are my units? So that's a rate. So it's going to be meters per year, okay? Because that's my height, and that's h and t. So it's going to be meters per year, okay? But actually, they want it in centimeters per year. So what we need to do is to get it in centimeters. From meters to centimeters, we need to times by 100, right? Because obviously 100 centimeters are in a meter, and so to get it from meters to centimeters, we need to times by 100, and then that'd be 15.27 centimeters per year. And that rounds to 15.3, okay? And that is the answer there. Cool. There we are. Then, according to the model, there is a limit to the height at which the plant can grow. So it's talking about limits again, the limiting value, the sort of the long-term value, okay? There's a limit to what the height the plant can grow. So it's saying that over time, over a huge amount of time, eventually there'll just be a cut-off point. The plant will grow no more. So there's an end point, there's an end value, there's a limiting value, right, to h. So the value of the limit then, well actually, that's when t goes to infinity again. The time goes very large over time, so then that means the exponential, the exponent e to the negative 0.2t will go to 0, okay? And so that means that therefore h is going to be 2.3 take away 1.7 of e to the negative 0.2t, but that will go to 0, okay? And so therefore that would just be 2.3. So that is the value, okay? So that is the maximum height you can think of that the plant will grow to. 2.3 meters, and there we are. Okay, we've got one final question here. So we're told here, in a simple model, the value of a car depends on its age. Quite similar to the earlier question we looked at to do with the car. So the value of the car in years, we're given the following information. The value when it's new is £20,000, and the value after 1 year is 16,000. Part A, it says use an exponential model to form a possible equation linking v with t. So the value linked with t. But it says use an exponential model. They've not actually told us what the equation needs to look like per se. But what you need, as we talked about earlier, an exponential model in general, we say that y is ae to the bx. Okay, that's the typical exponential model we use. And you have to make sure you put these unknown constants in. Okay, because if you just took e to the x, that's only one type of graph. Okay, but we need to account for the situation by adding these variables in, so a and b. So that's my general model, okay? But obviously we don't have y and x, we have v against t, so it's ae to the bt, okay? So now we just need to find a and b to get the actual model. But we're given these two bits of information. So firstly, the value when it's new is 20,000, but when it's new, it has no age, so the age t is 0, right? So then v will be 20,000, okay? And so we can sort of substitute that in then. So if t is 0, v is 20,000. And so if we plug that in, 20,000 is going to be ae to the 0. Okay, b0 is just 0. Well, that's just a, right? E to the 0 is 1, so we just get a is 20,000. And so actually we can write our model as 20,000 e to the bt. And now we just need to find b. Okay, that's where this next bullet point will come into play. We're told the value after 1 year is 16,000. So that means after 1 year, t is 1. So v is 16,000. So now we can substitute that in. So that means when t is 1, v is 16,000. So if we plug that into my formula, my model, my equation here, that means that 16,000 is going to be 20,000 e to the, well, bt, if b is 1, it's just e to the b. Okay, e to the b lots of 1, which is b. Okay, and so what we can simplify this to saying that if we can say that e to the b, if we could do 16,000 divided by 20,000, right? Because I'm going to solve for b, so I need b on its own. If I simplify that, I get e to the b is at 4/5. Okay. Now at this point, you actually can't solve it yet. I still wanted to include a question, even though you technically can't do all of it, because it's still quite useful, in my opinion. What I've done for now is giving you the solution. So if e to the x, or e to the, here we have e to the b, if e to the x is 4/5, then the solution is b is minus 0.223. So you could just take that for granted for now, okay? So b is minus 0.223, okay? That's the solution. I've given you that. But you can solve, we will look at solving that later on in the chapter, okay? You will, but for now, that's the solution, which means that v is going to be 20,000 e to the bt, so e to the negative 0.223t, okay? Okay, you can do the rest of the question though, okay? The rest of the question you can do, so no worries about that. Okay, that's the model then. So again, if it says exponential model, you should be thinking ae to the bt, okay? You should be thinking of an equation like this, okay? The following, then we're told the value of the car is monitored over a 10-year period. The value after 10 years, so t is 10, the value is 2,000. So it said evaluate the reliability of your model in light of the information. Well, we need to substitute this in. So that means when t is 10, v is 2,000. That's what we're given. So what you could do is substitute either v in or t in, okay? But let's substitute t in. It's a lot easier to solve for v than t. So if I sub t in, let's see what happens. So then v is 20,000 e to the negative 0.223 lots of 10. If I put that in the calculator, I'll get v to be I'll get v to be 2150.57, okay, to 2 decimal places. So that's the price. So as a price, it's 2150.57 pounds, okay? So compare that to this, okay? Compare 2,000 to 2,150. Is that, so in terms of the reliability, how close is the true answer of 2,000 compared to the model's prediction of 2,150? Now, actually, you could argue it both ways. The mark scheme is, as long as you actually justify your answer, you could either say the model's not reliable or it is reliable. This is actually kind of a bit subjective about how reliable it is. Some people might argue is that actually 2150.57 is quite close to £2,000. So therefore the model is reliable. You could say that. Alternatively, you might think it's too far. 2,150 is too far away from 200. You might think if it's £150 off, it might be quite significant. So you could also argue it's not reliable because it's not close enough. It's too far away from 2,000. It actually, in this particular instance, there is leniency. What you can do, sometimes there isn't no. Sometimes if the value is quite close, say for example if we had £2,002, you do have to exercise a bit of common sense and realise that's pretty damn close to 2,000. So the mark scheme will not allow you to say, oh, maybe it cannot be reliable because it's too close. But you can consider the percentage error if it helps. So the percentage error, obviously that would be 2,150 take away 2,000 over 2,000 times 100, and so that would be roughly 7.5%. Okay, roughly. So you're 7.5% off the true value. Again, that's subjective. Some people might think it's too much, but some people might think, oh, like it's not that much away. Like if it's generally, if you've got less than 5% error, it's pretty good. Like you don't want to say it's bad, okay? But if it's like, especially if it's like above 20%, it's rubbish model. If it's above 20% error, it's rubbish. But in this sort of region, you can debate it either way, okay? So yes, so that's the idea. So you can so you could do either way. You could say it's quite close or not close enough. So it's reliable or it's not reliable for that reason. But as long as you give a reason, that's all that matters. Okay. Right, then part C says the following information is available for car B. So all of this was for this car A. Okay, it's for car A. Now it's talking about a different car. We're told this car has the same value as car A when new, and the value depreciates more slowly than car A. Right, I'm going to do that up here. So remember, so if we have V is, again, as I remind you, the equation for V was 20,000 e to the negative 0.223t. That's what the equation we worked out in part A. We're told that it has the same value when new. So that means when t is 0, right, for car, so this is car A, for car B, it has the same initial value. So then if we substitute t0 into here, well, it still has to be 20,000. So it still has to be 20,000 in front, okay? 20,000 E. Okay. But we're told the value depreciates more slowly. So again, the key idea is it's talking about rate. It's more slowly, the rate, okay? So it's saying that for this car B, it needs to go down at a smaller rate, okay? Now, that's going to hint about the derivative, okay? So that's going to be that dv dt, okay? If we were to work out dv dt, okay, so dv dt, if we were to do that, differentiate this expression here, well, that's going to be minus 0.223, then v, okay, v. That's telling me that for car A, the value is decreasing by 0.223, okay, that's what it's saying, decreasing at a rate of 0.223. That's what that means. Okay, so hopefully you can see then, if we want the value, if we want the value to decrease more slowly, so we want to decrease at a smaller or slower rate, that has to be lower then. It has to be lower than 0.223. So this number minus 0.223, the exponent here has to be closer to 0. So it has to be something like 0.01, okay? Because 0.01 is, it's closer to 0 than 0.22, okay? That would mean that if we had minus 0.01t, the rate of decrease is now 0.01. That's a smaller rate than 0.223. So my answer is now, to answer that question, do it down here. How would I adapt the equation? Is I would change the value of the exponent. What was it? Minus 0.223. To be closer to 0. Okay. As in, then if it's closer to 0, it'd be smaller in size. Okay. So it'd be a slower rate. Okay. And so that's my answer there. Okay. Cool. But also big. I don't want to overcomplicate it. But pay attention to the wording. I said closer to 0. I do not want to say make it more positive. Okay. If you said to make the value more positive, then what could happen is your rate maybe could be positive 0.223. That would then be increasing. But remember, I still want the overall derivative to be a negative value. So it still has to be less than 0, okay? Because then if it's negative, it'd be decreasing. I still want it to decrease, but decrease at a smaller rate. Hence the physical number, what still has to be negative, has to be like closer to 0. So it's a smaller physical size. So I want to pick a number that's smaller than 0.223. For example, 0.01. That's a smaller rate that will give me a smaller rate of decrease. Okay, so there we are. So that's exponential models. We are going to look more into exponential models when we look at logarithms. So we will be revisiting this later on in the chapter. But for now, hopefully you get the essence of an exponential model. So stuff like the limiting values, the initial value in t0, what the numbers mean. So again, like this, the exponent generally means the rate of increase or the rate of decrease. The number in the front means the initial value and stuff like that. Okay. And yeah, so I'll see you next time.